Hello, welcome to this final pre-lab video for this semester. And so in this particular video, we are going to be looking at the electrochemistry experiment. Now, this is a great experiment to end on. This is personally one of my favorite experiments. And one of the reasons why this is such a fun experiment for me is it kind of taps into that kind of builder maker kind of side that a lot of us have, where we see these things in pictures and we go, I wonder if I could do that. Well, in this case the answer is absolutely, we totally can do this. So the topic here is electrochemistry. What we are going to be doing though is we are going to be making voltaic cells. So just recall, a voltaic cell is one that leverages the half cell method, where we're going to have the cathode on one side and the anode on the other side, and we are going to hook them together, and voltage is going to pass because there will be electrical current traveling from one side to the other. And so we're going to have alligator clips, wires to connect the electrodes to each other, a salt bridge in the middle to keep the cells from becoming polarized, and we're going to measure the voltages here. So you've already done and had experience with calculating cell potentials. The purpose of this experiment is we're actually going to do that. So we're going to create a series of half cells. And so the series of half cells that you're going to make a silver half cell, you're going to make a copper half cell, you're going to make a lead half cell, you're going to make a tin half cell, and you're going to make a zinc half cell. And what you're going to do is we are going to measure the voltage of all of these different cells as they react with copper. Copper is going to be kind of our standard here. So if you go back to the introduction here, we told you that the copper is going to be a 0.34 voltage. 0.34 volts is going to be the standard voltage that we use. We are going to use that voltage plus the results of what happens when we hook that copper up to other things to figure out what the cell potentials for these other ones would be. So yes, I know that you can go and you can look up the silver half cell potential, the lead half cell potential, the tin, the zinc, and so on. But we're going to do this to kind of validate that our technique works. And what you'll see is that we actually get pretty close. So what are some things that you're going to need and things that you're going to do? Well, one of the things that we're going to do is we are going to be using differential voltage probeware. So we're going to need vernier stuff. So between you and your lab partner, one of you is going to have to be able to hook up to the interface and do the data collection. Unlike some of the other times we've used vernier, the data here are pretty reliable. So the calibration component is actually really easy. You just take the two alligator clips and you clip them together, and it should read 0 voltage. If it doesn't read 0 voltage, then we have to recalibrate. But it should read 0 voltage when we clip those two clips together. And then, so in procedure 1, you're going to make a series of electrochemical cells. And what you're going to be collecting off of those electrochemical cells is you are going to measure the voltage. And so again, since copper is kind of our standard electrode here, we are going to hook the other 4 cells up to the copper, and we are going to measure their voltages. Now, depending upon where the copper is, that's going to impact how we do the calculation. Because ultimately we are going to be using the cell potential equation, cell potential being the reduction potential of the cathode minus the reduction potential of the anode. So Whether the copper is the cathode or the anode tells you where to put that 0.34 volts in the equation to figure out the other cell's value. And so if you go down to the results in the analysis here, you're going to be asked to give cell equations, and then you're going to be asked, okay, calculate the electrode potential for silver, for lead, for tin, for zinc, put them in ranking order. So we're looking for increasing ease of reduction. So this is more or less very similar to the oxidation series that you did in the previous lab. So the things that are going to be the most easily reduced are going to be the greatest oxidizing agents. So that's part one. In part two, you're going to make concentration cells. Now, you learned about concentration cells in in lecture. That's where you've got the same chemical reaction taking place, but you have a difference in concentration between one of the cells and the other cell. If the two cells are at the same concentration, no voltage will flow because they're at equilibrium. But if one cell is different in concentration from the other, they will react to seek to even up their concentrations. And then once again, when they're at the same concentration, the thing will stop. Now, the way that we are going to do this is we are not actually going to make a concentration cell in kind of the traditional sense where we have, say copper on one side and copper on the other side. But what we're going to do instead is we're going to manipulate the concentrations of the two cells. We're going to effectively poison them by adding a high amount of of ammonia solution. And so what you know is that zinc and copper, you know this from your qualitative analysis, both of them will chelate, will complex to ammonia. And so what happens when that complex forms? Well, that means that the concentration of the free copper or the free zinc is going to decrease, and we should see a movement in one direction or the other. And so if you go to your data for procedure 2, it's going to basically just, okay, here's what it was before. What happened to the cell potential when we added it to the copper? What happened to the cell potential when we added the ammonia to the zinc? And then this analysis question here. This next to last analysis question is asking you to explain why you saw what you saw. The last procedure is not actually a procedure that you will do. It is a procedure that I will do. And it's probably something we will start the experiment with, and that is an electrolysis demonstration. In the electrolysis demonstration, I am going to take a solution of potassium iodide. I am going to put 2 very large carbon electrodes in there. Now, the reason for the carbon electrodes is that carbon is still electrically conductive. However, carbon does not react with either of these, does not react with potassium, does not react with iodide. And so we're going to hook these carbon electrodes up to a power source, and that's going to provide the electricity, the energy. We are going to do electrolysis of the potassium iodide solution, and we're going to observe what happens, and then we're going to try to explain what happens. And so, again, in the data results here, all that we're looking for are observations. What do you see? And then the very last question here is kind of explain what you saw, write the reaction equations. So the experiment itself, like I said, it's a lot of fun. You're going to be working not just with a partner, but you're also going to be paired with another group to share cells so that we don't have quite as much waste, and so that we are able to kind of keep things going. So that'll save you some time because you won't have to make all of the different cells. The last thing that I'll talk about here is the post-lab questions. The post-lab questions are basically just asking you to, so in the first couple here, use your values from the data section to calculate cell potentials for some electrochemical cells that you did not make. Predict some observations of what would happen if this situation were to take place. And then talking about just some general kinds of questions related to electrochemistry and electrolysis. So that's it. This is what we're going to end with. This will be our last wet lab, especially since we've already finished the lab practical. So this will be a good way to end things. And that's really all I have to say here for today. So if you have any questions, feel free to reach out to me. Otherwise, I'll see you next time in lab.